weekly seminar. Today's presentation will be hosted by Daniel Kane. Daniel is a professor from the University of California, San Diego. Daniel, the floor is yours.
Hi, thanks. Let's bring up my slides. I would like to talk to you today about algorithmic high-dimensional robust statistics. This is on a body of work that has taken place over the last 7 years or so. This is based on work with Ilias Diakonopoulos and a bunch of other people. I've been involved in a lot of it, though not all of it. I guess I cite some of it, but not everything. Just there's been a lot of people contributing to all of this. In any case, so for background, what is statistics? In statistics, there's some unknown distribution D. Perhaps it is from some class of distributions. It's a Gaussian or something like that. You draw a bunch of IID samples from this distribution, and then you do some processing on those, and you want to learn something about the distribution. You want to get an approximation to the distribution. You want to approximate its mean or some other parameters. But by processing the data points, you want to hopefully learn something about the underlying distribution that produced them. Okay, what's robust statistics? Same basic premise. You have an unknown distribution D coming from some class. You take a bunch of IID samples, but you assume that a small fraction of these samples may have been corrupted. Their values got changed. Perhaps they're now very far away from everything else. And what the question is despite these corruptions, you'd like to still be able to learn something about the underlying distribution that generated at least the uncorrupted samples. And so the question is, statistics has been studied for 100 years, and we have a pretty good understanding of a lot of questions about what properties of distributions you can learn from IID samples. The question here is, what can you learn from IID samples, even if a small fraction of them have been corrupted? So to see what type of corruptions we're talking about, there are a few sources of corruption that you might consider that are sort of in increasing levels of seriousness. At the base level, you might just have model misspecification. So the theory that you're trying to use says that these points should be Gaussian distributed, but in the real world, no distributions that you see are ever going to be actually exactly Gaussian. And so the fact that the process that's producing the samples that you're seeing produces samples from something that's not quite Gaussian can be thought of as a source of noise. Some of the samples, rather than coming exactly from this Gaussian, come from some slightly different distribution instead. A slightly worse thing that you might consider is data contamination, that most of your samples do come from a process that satisfies all of the assumptions that you wanted, but occasionally there's contamination. Occasionally the process that was supposed to be producing these samples gets messed up. You get a sample from some other distribution, the machinery generating this data messed up, something like that, and you end up with some kind of samples that are just completely different from the ones that you're expecting. And finally, perhaps the most severe is adversarial contamination, that somebody is actively trying to interfere with your ability to do statistics. We assume that they can only influence a small fraction of the inputs, because otherwise, if they can just control all of the samples that you see, there's nothing that can be done about it. But if they control a small fraction of the samples, maybe they are trying to tweak the samples that they have control over in just the right way to fool whatever processing you're trying to do. And so we'd like to have, methods of doing statistics that can deal with these kinds of errors. Okay, so in terms of models, there are sort of two that are most basic, and we are really not going to be distinguishing between these much in the talk, but one of the most basic things to do is what's called Huber noise, where what you do is you get IID samples rather than getting samples from the distribution D that you care about. You get samples from a mixture where with probability 1 minus epsilon, it returns a sample from D, and with probability epsilon, it returns a sample from some other distribution E, which can be thought of as errors or noise or something like that. And so a 1 minus epsilon fraction of your samples come from the distribution you care about, and an epsilon fraction from something else. A slightly stronger notion of noise, what's been known as the strong contamination model. Here, firstly, you take IID samples from the distribution D, the one that you care about. And then an adversary is allowed to inspect these samples, pick any epsilon fraction of the samples that they like, and change those to some other values, whatever they think will most interfere with your ability to do statistics. And the strong contamination model is a little bit worse to deal with for a couple of reasons. Firstly, it's adaptive. They can choose what corruptions to make based on having seen the good samples. And secondly, the Huber model only adds errors, whereas the strong contamination model replaces good samples with bad samples. So not only can it add errors, it can also sort of delete good samples. And both of these make it a little bit more difficult to deal with. Okay, so that's the sort of background for the kinds of problems that I want to solve. So to get a feel for what's going on here, let's talk about perhaps one of the simplest problems in statistics, which is Gaussian mean estimation. So here your good distribution D is a normal distribution with mean mu and identity covariance sitting in D dimensions. And so traditionally, you've got a bunch of IID samples from D, and your goal is to estimate mu. And if there are no errors, the solution is hopefully well known to most of the people here. You should use the sample. This has error that with high probability is on the order of square root D over epsilon. And you can also show that in some very real sense, this is essentially the optimal estimate, or this is basically the best thing you can do. But it gives you a pretty good estimate. The error goes to 0 as the number of samples goes to infinity. It's great. Okay, what can we say about robust Gaussian mean estimation? So it's the same setup. You've got D, it's a Gaussian with identity covariance and unknown mean. You want to estimate the mean mu from noisy samples. So again, you've got these samples and some small fraction of them have been corrupted. And of course, in this case, unfortunately, the sample mean no longer works. In fact, the sample mean is really, really bad if you want to robustly estimate things, because if you corrupt even a single sample, badly enough, it can move the sample mean wherever you like. And so this traditional sample mean statistic, doesn't work. And so the basic question to get started is, what can we do instead if we're trying to do robust mean estimation? Okay, any questions? All right, so before we get into designing, algorithms and statistics for this, it's helpful to look at the information theoretic limits. And in particular, there's a big difference here from the non-robust case, where in the non-robust case, if we got more and more and more samples, the error would go to 0. In this case, that's not possible, because if we take our samples, the good samples, we take them from this normal distribution. Now, if we had a clever adversary, what they could do is they could pick another Gaussian that is very close to the original in total variation distance, and they could move some of the samples so that the samples from one side, they sort of move them over to the other, and they take a distribution that looked like normal with mean mu, and by changing only a few samples, they make it look like they're getting samples from a normal distribution with mean mu prime. And essentially what this means is that if you have an epsilon fraction of errors, you cannot hope to learn the underlying distribution to total variation distance better than epsilon. Because if you have two distributions with total variation distance epsilon, one way of interpreting that is that means that you can think of these distributions as being the same except for an epsilon fraction of the time, you get samples in one place instead of the other. And so if there's an epsilon fraction of errors, you can just move from one to the other and you can't tell which was the ground truth and which was the error. And so in particular, what this means for Gaussian mean estimation is that, well, for Gaussians with identity covariance, the total variation distance is roughly proportional to the L2 distance between the means. So if we're trying to learn the mean of a spherical Gaussian with an epsilon fraction of errors, we cannot hope to learn the mean to L2 error better than about epsilon. And so that's sort of an underlying limit that we just can't beat no matter how many samples we have. Okay, so that's a limit, but on the other hand, is O of epsilon error possible? And here it's useful to start by looking at the one-dimensional case. So here you want to estimate the mean of a one-dimensional Gaussian. And what you need is an estimator that is not sensitive to outliers. The problem with the sample mean is that it's very sensitive to outliers. If I have just a few samples that are very, very far from all the others, they're going to mess everything up. And so there are a few ways to do it. I mean, the most natural thing maybe to try is some kind of outlier removal or some kind of trimmed mean kind of thing. The trimmed mean is where you just throw away the tails of the distributions and compute the sample mean of whatever's left. And these estimators do reasonably well. But a little bit more classically and a little bit more effective is to instead use the mean. So the theorem is that if you have more than about 1 epsilon squared samples from an epsilon corrupted Gaussian, then with high probability, the sample median is within error O of epsilon of the true mean. And the proof of this is relatively straightforward. So with high probability, at least a 1/2 plus epsilon fraction of the uncorrupted samples are less than mu plus 10 epsilon. And this is just because, I mean, each sample has a slightly bigger than 1/2 probability of being smaller than mu plus 10 epsilon. And this is just, we have a binomial, and if you have at least 1 over epsilon squared many samples, you're going to approximate the true fraction to within a small amount, and so this should hold. But if we introduce an epsilon fraction of errors, that can't change the fraction of samples that are less than mu plus 10 epsilon by much. And so in particular, if this were the case, then even after we've added errors, at least half of the corrupted samples, half of the total samples after corruptions, are still going to be less than mu plus 10 epsilon. And in particular, if that's the case, that means the median of the corrupted sample set is going to be at most mu plus 10 epsilon, because at least half the samples are less than it. Similarly, with high probability, the median is going to be at least mu minus 10 epsilon. And if both of these hold, that means that the sample median is within 10 epsilon of the true. And so that shows you that you get error at most 10 epsilon with high probability. Okay, so that's what happens in one dimension. The big question next is, how do you generalize this notion of the median to higher dimensions? And well, there are a few natural ways to do this, and maybe the most obvious is the coordinate-wise median. So for each coordinate, you get a bunch of samples. We look at all of the first coordinates of all of our samples. We take the median of those. That's a good approximation to the first coordinate of the mean. And then you do the same thing with the second coordinates, and the same thing with the third and fourth and fifth and sixth, and so on. Oh, sorry, there were some old comments that I missed. So there's a question about, do we assume that epsilon is known? And I think for the moment, it is probably best to assume epsilon is known. Most of this theory can be done in the case when epsilon is unknown, but it requires a little bit more. Okay, sure. So back to what I was saying. So we can do a coordinate-wise median, and this does okay at least. The obvious conclusion that we can draw from the one-dimensional case is that for each coordinate, that coordinate of our samples is just an epsilon corrupted Gaussian, and so taking the median over that coordinate learns that coordinate of the mean to error O of epsilon. Unfortunately, if we have a d-dimensional vector and we learn each coordinate of that vector to error epsilon, then we've learned the full mean vector to error O of epsilon root d, at least in the L2 norm, which is the one that we care about here. And unfortunately for us, that is too much. And also, unfortunately, it's not hard to find examples where you really do get epsilon root d error using this coordinate-wise median. Okay, so if coordinate-wise median doesn't work, how else could we generalize this? Well, the coordinate-wise median, what it does is it considers the medians of each of the coordinate projections. Now, that's not the only projection we could consider. We could also consider the medians in other directions. So in particular, we've got our noisy samples, xi. For any unit vector v, we can take the dot products v dot xi for all I. And these are going to be epsilon noisy samples from the one-dimensional Gaussian with mean v dot mu. If we take the median of that, well, this will give us some median value m sub v, and with high probability, that is going to be an O of epsilon estimate of v dot mu. And so the question is, if we have all of these sort of estimates of these one-dimensional projections, can we piece them together to get an estimate of mu? And so what we have is for each v, we have an mv, so that the difference between mv and v dot mu is O of epsilon. And what we can hope to do is we can hope to find some mu hat, where for every unit vector v, the difference between mv and v dot mu hat is O of epsilon. And of course, if we had the sequence of mv's for which this works, there is going to be some mu hat for which this holds, because mu hat equals mu is such a vector. But the claim is that if you find any mu hat which satisfies this system of equations, that's going to be a good approximation to mu. And for that, we need to think about how big is mu hat minus mu. And in order to get a bound on it, what we're going to want to do is we're going to want to use the sort of duality of the L2 norm. The fact that the L2 norm of a vector is the supremum over directions, v, of v dot x. And the point is that if there is some error between mu and mu hat, the error has to be in some direction. And in particular, applying this to mu dot mu hat, the L2 norm of mu dot mu hat is the supremum over unit vectors v of v dot mu minus v dot mu hat. But v dot mu and v dot mu hat are both close to m sub v. And so by the triangle inequality, that error is going to be O of epsilon. And sort of the fact that we have checked every single direction v means that there's sort of no direction in which our error is allowed to be too large. And in particular, this technique does actually give us a way of computing an estimator that achieves O of epsilon error. And so this has been known for a while. So this is statistically optimal. Remember, we knew that there was a lower bound of O of epsilon. So at least up to constants, this is the smallest error that you could hope for. It's also similar to a more classical estimator known as the Tukey median, which again, sort of looks at every single direction and tries to ensure that there are the same-ish number of points on each side, but sort of arranges those tools in a slightly different way. But also, again, gets O of epsilon error. Okay, so great, we have an error that learns the mean to error O of epsilon, and that's the best we can hope for statistically. Unfortunately, there are computational issues with this. And we should ask ourselves the question, if we wanted to compute this estimator, how would we do it? Well, I mean, it seems straightforward. For all v, we compute m sub v. And then we have the system of inequalities that we need to find mu hat. And that system of inequalities, it turns out, is just a linear program. So that's not too hard. The problem here is that we need to, if you take literally my prescription for computing mu hat, you need to compute mu sub v for every unit vector v, literally infinitely many values. Now, it turns out that you don't literally need every single value. You just need enough directions v that somehow, checking that mu and mu hat are close in every direction that we have checked is good enough to guarantee that they're actually close. And for that, it suffices to take only 2 to the O of dimension many v's. Unfortunately, I mean, it really does take that many of them. If you take a sub-exponential number of v's, there are going to be directions in which there might be errors where the projection of that error onto every one of the directions you've checked is small. And so it really does seem that generalizing this kind of statistic, although it's possible to compute it in finite time, it really seems that it takes time exponential in the dimension. And in fact, computing the Tukey median, this sort of classical analog of this cover idea, that turns out to actually formally be an NP-hard problem. And so computing these kinds of estimators that look at lots of different directions in order to get O of epsilon error, these seem to not be computationally feasible. Now, another thing that you might try is outlier removal. So this other technique that we had in one dimension was some sort of trimmed mean. You throw away outliers that are too far from the mean. And this, again, has a nice analog in d dimensions, but it's not quite as effective. So points in a d-dimensional Gaussian are at distance roughly square root d from the mean. And in fact, for high dimensions, you can roughly approximate a Gaussian as a spherical shell of radius root d. And so that means that if there are outliers that are further from the mean than approximately root d, it's pretty easy to identify those as outliers and you can just throw them. That's relatively easy to do. It's what's been known in the literature as naive filtering. However, if you have errors that are at distance root d from the mean, it's hard, at least on an individual level, to detect those as errors because they're just as far from the other samples and just as far from whatever approximate mean you are using as basically all of the other samples that we're seeing. And so you can't really remove those as outliers efficiently. But on the other hand, if you have an epsilon fraction of outliers that are at distance square root d from the mean in the same direction, that's enough to corrupt the sample mean by epsilon root d. And so if all you do is naive filtering, you can end up with an error as big as epsilon root d. And this is basically the state of affairs. From the 1960s, when people first started studying these questions seriously, through 2015, there were 3 kinds of algorithms to solve high-dimensional robust statistics problems. There were heuristic algorithms, ones that sound like they have some good ideas behind them, but don't really have provable guarantees. There are algorithms where the worst case error scales polynomially in the dimension. Things like naive filtering or coordinate-wise median fall into this category. And then there were those where the runtime was exponential in the dimension, things like the Tukey median. And none of these are really that satisfying. I mean, basically you're deciding between having huge errors that potentially become useless if you're working in sort of high dimensional big data scenarios, and algorithms that are exponential, so that in high dimensions, you'll never actually be able to run. And so this changed in 2016. Were a pair of papers that got around this. And so the result is that there exists a polynomial time algorithm where if you're given samples from an epsilon corrupted Gaussian, say with mean, mu, and identity covariance, it computes an estimate of mu, where with high probability, the estimate has L2 error, not quite O of epsilon, not quite the optimal, but O of epsilon square root log 1 over epsilon. So this is the big result, and this is what I'm going to spend most of the rest of the talk. Okay, any questions? All right. So I will say that this has been improved a little since then. So with some later improvements, you can get basically an optimal number of samples, O of D over epsilon squared, actually a tiny bit better than that. You can get near linear runtime, O tilde of D times N. However, there is evidence that getting error better than epsilon square root log 1 over epsilon is actually hard. There may well not be polynomial time algorithms that can achieve that. Okay, so how do we do this? The basic intuition is, again, with this naive filtering algorithm, we've noted that you can't remove outliers on an individual basis. Errors that are at distance root D from the mean are somehow statistically indistinguishable from inliers. Those are not specific, things that are at distance root D from the mean are not particularly unlikely samples to have showed up. There's no sort of a priori reason why you should consider it to be an error. However, if you have a bunch of errors like that in the same direction, they are enough to corrupt the sample mean by epsilon root D. And the good news, though, is that we don't need to detect individual outliers. In particular, if you have a bunch of errors at distance root D in sort of random directions, then those errors are likely to cancel out. And if they cancel out, we don't really care because they don't really affect the sample. And so all that we need to detect are not the individual errors, but we only need to be able to detect if there's sort of a conspiracy of outliers, a bunch of outliers in the same direction that are enough to actually change the sample mean by a notable amount. And the next piece of good news is that we can actually detect such conspiracies. In particular, if you have enough errors to corrupt the sample mean by some notable amount, then they have to corrupt it in some direction. There has to, and this is again the duality of the L2 mean norm, that if there's a big difference between the mean and the sample mean, there has to be some V where the difference, in the V direction is quite large. So there has to be some unit vector V such that V dot mu hat is far from V dot mu. And in particular, that means there has to be many errors that are far from the mean in the V direction. And finally, the key insight is that these errors must cause the variance in the V direction to be substantially larger than they ought to be. And that is a thing we can detect. So slightly more formally, if we have an epsilon fraction of errors that move the mean by delta in the V direction, then on average, these errors need to be at a distance about delta over epsilon from the mean. And what this means is that the addition of these errors will increase the variance by something like delta squared over epsilon. Now, things are not quite that bad because, maybe in addition to adding some errors, they removed some good samples. But a Gaussian is pretty well concentrated. Even if you remove, the epsilon furthest from the mean samples, that's not going to decrease the variance by too much. And in particular, you can show that if delta is much more than, say, epsilon square root log 1 over epsilon times some large constant, then the variance of the corrupted set of samples will be substantially larger than it should be. In fact, instead of being 1 like it would be for spherical Gaussian, it will be 1 plus omega of epsilon log 1 over epsilon. It will be substantially larger in that direction. And so this gives us the starting point for an algorithm. We take a set of samples, we compute the covariance matrix. We then use principal component analysis to compute the largest eigenvalue lambda of that covariance matrix. And if lambda is smaller than 1 plus some large constant times epsilon log 1 over epsilon, that's enough to certify that the sample mean is close to the mean. And in that case, we can just return the sample, because in that case, there can't have been a direction where the errors corrupted the mean by a lot in that direction, because that would have caused there to be large variance in that direction, and that would have been detected by this eigenvalue computation. So that's the first piece of good news, that if the covariance matrix is small, we at least have a way of showing that this sample mean is actually close to the truth. The other thing that we need to figure out, though, is, what happens if this eigenvalue is large? What happens if there were enough outliers to corrupt the sample mean? Can we do anything? And in that case, we've got another piece of good news, which is that if the eigenvalues are large, that means there has to be some direction v, where the empirical variance in the v direction is substantially larger than it should be. And the fact that we have that vector means that we sort of know a direction where it at least looks like the adversary is trying to corrupt our mean in that direction. And that gives us a better way to look for errors. And in particular, in order for the variance to be that large, it has to roughly be that an epsilon fraction of our samples are at some big distance delta over epsilon from the mean in that direction. And almost all of the samples that are too far from the mean in that direction will be corruptions, will be bad samples. And so if we can filter those out, if we can remove those outliers and repeat, we'll be in good shape. So more specifically, how do we do this outlier removal? We'd like to find some threshold t so that a majority of the samples where the absolute value of v dot x minus mu is bigger than t are outliers. Now, how do we do that? The good samples are Gaussian distributed. So the fraction of good samples where v dot x minus mu is bigger than t falls off like e to the minus t squared over 2. So the claim is that if an epsilon fraction of outliers increase the variance in the v direction by some large constant times epsilon log 1 over epsilon, there has to be some threshold t such that the fraction of samples with v dot x minus mu bigger than t is at least 100 times e to the minus t squared over 2. And since only 1 times e to the minus t squared over 2 can be good samples, 99% of those samples must be corruptions. So if we can know this claim, we just have to find a threshold for which this holds and then throw away all the samples that are too far. Now, how do we prove this claim? Well, a large variance means that the expectation of v dot x minus mu squared is substantially larger than it should be. We need to relate this expectation to some tail bounds, some probabilities that v dot x minus mu is large. And we can do that with the following general identity. The expectation of x squared is the integral from 0 to infinity of 2t times the probability that the absolute value of x is bigger than t. And so, in particular, if we compare the variance of our sample set to the variance of the Gaussian distribution, the difference is going to be the integral of 2t times the difference in these tail probabilities. Now, we know that because we got x by corrupting an epsilon fraction of the samples, for any t, the difference in those tail probabilities is going to be at most epsilon. So for small values of t, say t less than 10 root log 1 over epsilon or something like that, the contribution to this integral is going to be an integral of 2t times epsilon. And so you get like O of epsilon log 1 over epsilon from those terms. On the other hand, if there are no t's for which this tail bound is not satisfied, there's no t's for where the probability that x minus mu bigger than t is larger than e to the minus t squared over 2, then the contribution to our integral from the tails is also going to be small because there are going to be so few samples. And just because the tail bound should say that, already at 10 square root log 1 over epsilon, there's only epsilon to the 100 many samples, and it falls off quickly from there. And so, in particular, unless this threshold is violated, unless there's some threshold where we've got many points beyond that, then there's no way that the variance can be substantially larger than 1. And so that completes the proof that if the variance is large, if we're seeing samples from an epsilon corrupted Gaussian, then we have to actually be able to find some threshold where almost all of the samples beyond that threshold are outliers. Okay. Now, there are a couple of technical points with the presentation that I just gave. Firstly, the algorithm doesn't actually know the value of mu. So I can't say, is this sample v dot x minus mu bigger than t, because I don't know the value of mu. But it's good enough if I just take an estimate of v dot mu. I could take a median of v dot the samples. That should be good enough. The analysis is complicated a little bit by this, but it's not hard to work out. A second technical point is that I need this analysis to work not with the sort of underlying distributions that I'm seeing samples from, but I need it to work with high probability in every direction v, even when I have only a finite number of samples. And this requires a somewhat careful analysis using some tail bounds, and it can be done. The details are not that bad, but it doesn't fit well into an introductory hour-long talk. So this leads to the algorithm that's known essentially as the filter algorithm. The input is a set of samples S, and what you do is you compute a sample covariance matrix. If the top eigenvalue is small, you return the sample mean of the set. Otherwise, you let V be a biggest eigenvalue, you dot all the samples with V, and you remove the outliers. You find some threshold where we know most of those samples are outliers, remove all the samples further from the mean than that, and then you rerun the filter algorithm on that new set. And that's the algorithm. To show that it works, as we've already shown, if the top eigenvalue is small, this certifies that the sample mean is reasonably close to the true mean. And on the other hand, if the top eigenvalue is large, we've shown that if you're careful with your outlier removal, you can essentially guarantee that you remove more bad samples than good samples. And then when you make your recursive call, it is on a less corrupted version of your original set, at least if you define the corruption parameter carefully. And so, you either get a less corrupted sample, and that'll do even better than your original one, or you get an estimate of the true. Okay, so that is the filter algorithm. One natural way to try and generalize this is you want to know how much this algorithm relies on the fact that your samples are Gaussian. And the more modern way of looking at this is we say that the set S is epsilon delta stable with respect to some mean mu. If for any subset S prime that consists of at least a 1 minus epsilon fraction of the samples, the mean of S prime is within delta of mu, and the covariance of S prime is within delta squared over epsilon of the identity in the operator. And so effectively what this says is that, that the mean and variance of S are not affected too much by any epsilon fraction of the samples. And a generalization of the algorithm I was just talking about actually can work for in this sort of generality. If S is an epsilon delta stable set, there's an algorithm that learns an approximation to the mean with error something like O of delta from S, even if an epsilon fraction of the elements of S are corrupted arbitrarily. And roughly what this means is that if you have a distribution D where the covariance is close to the identity, and the epsilon tails of this distribution in any direction contribute no more than delta to the mean, then you can learn the mean to robustly to error roughly delta. So in particular, if D has bounded covariance, you can make do with delta O of root epsilon. And if delta is, for example, an isotropic log concave distribution, then you can learn to error O of epsilon log 1 over epsilon. Okay, so this is, the sort of very basic principles of this sort of modern theory of high dimensional robust statistics. There have been a bunch of other advances in the last 7 years. We can estimate covariances of Gaussians and some other distributions. You can robustly estimate a bunch of more complicated things, binary product distributions, Gaussian mixture models. You can do list decodable estimation. This is what happens when instead of a small fraction of errors, you instead have a small fraction of good samples and a giant sea of errors. You can do robust versions of various supervised learning problems like linear regressions, learning half spaces, stochastic optimization. We also now have a better understanding of which problems are hard and which ones aren't. And we think that some of the problems here are actually computationally difficult. In any case, I have some more slides, but I don't think I have the time. So I just want to, skip to the end, which is that there's a new book out. So Ilias Diakonikoulos and I have been working on this a lot for the last bunch of years. Have a new book that should hopefully be coming out later this year on exactly this topic. And there's an electronic version of the book that can be found in the link below. Okay, that's all I had to say. Are there any questions?
Thank you very much, Daniel. Okay, we are going to open the floor for questions.
Yeah, I have a small question, which is all you've talked about is at first you had two models, the Uber or whatever, and strong contamination. I think all you've said applies to like the worst one, where like the adversary can do like looks at the samples, decides what to do, etc. Is there any improvement you can get in the easier model, or is it pretty much all the same in terms of algorithms?
Are there improvements that we can get in the Huber model if we don't have that? A little bit. So in particular, I said that there's evidence that it's hard to get error better than epsilon root log 1 over epsilon for Gaussian mean estimation. That's only for, well, you don't quite need the full strong contamination model, but you need there to be both additive and subtractive noise for that to be difficult. In particular, there is an algorithm that shows that if you have only additive noise or only subtractive noise, but that's a weak error model. But if you have only additive noise, you can actually get error O of epsilon in polynomial time. So there are a few problems like that where we can do a little bit better if there's no subtractive noise. Okay, any other questions?
In that case, I've got another one. You mentioned the Tukey median. I have to say I never fully understood the definition of Tukey median, but like it's NPR, but is it like NPR like but also hard in practice, or is it one of those things where like it's NPR in the worst case, but like in practice it's kind of okay?
Is the Tukey median in practice hard to compute? So I mean, I guess it depends a little on what instances you want to look at in practice. I will say I've not seen the proof of NP completeness for this, and so I don't know, but and certainly like if you have samples from a Gaussian, we now know that it is not hard to approximately compute the Tukey median because you can do robust mean estimation and that ends up being pretty close. But I guess what I can say is that, as I mentioned, there is evidence that it's hard to robustly learn the mean of a Gaussian to error better than epsilon root log 1 over epsilon. And if on those instances you could compute the Tukey median, you could do better than that. And so we at least have some examples of reasonable average case instances where it is expected that Tukey median does not have polynomial time algorithms.
Thanks.
Okay, anyone else?
Okay, I think we don't have any further questions.
Point.
Yeah, looks quiet. All right, I think that's it. Thank you very much, Daniel, for joining today, and we appreciate your time for today.
Sure.
Cool. Thank you, everyone, for joining.